Okay, so let's do some problems with this free fall. So example number 1 says a ball is thrown straight up with an initial velocity of 17 meters per second. What is the maximum height attained by the ball? So if we throw the ball straight up with an initial velocity of 17 meters per second, I'm going to call upwards the positive direction. Again, you don't have to, but I'm going to call it the positive direction. So my initial velocity is a positive 17 meters per second. Now, they're asking us for the maximum height attained by the ball. So when we're talking about a height, that's a distance or a displacement in this case, okay? So since we have a displacement that we're looking for, I'm just going to put delta y equals question mark. Now, the reason I put delta y is because we're going in the vertical direction. You could put delta x too, that's totally fine, all right? But I do want to start kind of denoting which direction we're going because we are going to start projectile motion soon where we'll have 2 dimensions. So what is the maximum height attained by the ball? Now, that's all the information they give us, but remember, there are these things called hidden givens in problems like this. So we know that since the ball is under the influence of the Earth's gravitational pull, the acceleration of gravity is 9.8 meters per second squared. Now, it's directed downward, so I have to put that negative in there. So I know that the acceleration is going to be a negative 9.8 meters per second squared. And then also, I know that I'm looking for the maximum height. Remember, the special thing about the maximum height is that that object travels upwards, it stops at the maximum height, and then turns around and goes the opposite direction. So at the maximum height, the final velocity is 0. So we get final velocity equals 0. Now, the equation that we need to use is one of the constant acceleration equations because we have a constant acceleration, and it has to have initial and final velocity, our displacement, and our acceleration in it. So the equation you want to use is that final velocity squared equals initial velocity squared plus 2 times a times delta x. In this case, I used delta y. It's just the displacement, okay? So I'm going to rearrange this equation to solve for delta y. So I'm going to subtract initial velocity from both sides. So I get final velocity squared minus initial velocity squared, and then I'm going to divide by 2 times acceleration in order to get that delta y by itself. Now, something to note here is that I know that the final velocity is 0, so that's going to cancel out to make our math a little bit easier. So final velocity is 0, that cancels out, and then I will plug my numbers in so I can solve for delta y. So I get negative initial velocity is 17 meters per second. I'm going to square that, divided by 2 times a negative 9.8 meters per second squared. Okay, so notice how if I said that down was positive, acceleration would be positive, and then I would end up getting a positive v initial squared on the left-hand side in that middle equation because it would be subtracting a negative, because I would say that up is negative. So no matter what direction you say is positive, it still works, okay, which is good to note. So we end up getting 14.74 meters. Oh no, it's just meters because we're looking for a displacement. All right. So I'm showing you how those units cancel out. This squared goes to both this term and this term. I cancel out seconds squared, and then I also cancel out that meter, that squared with the meters down there, which is why you end up getting meters. All right, so that's the first example. Let's do another one. We have example number 2. An object is thrown off a cliff with an initial upward velocity of 15 meters per second. If the cliff is 100 meters high, how long does it take to strike the ground at the bottom? All right, so something like this, I'm going to draw a little picture to kind of show you what I mean here. So here's the ground. This object is thrown straight up at 15 meters per second, and then it goes up and then comes all the way down to the bottom like that, all right? So it's almost like you're leaning off the cliff and throwing the object straight up into the air. You're not throwing it out at all because that is motion in 2 dimensions, and we have not covered that yet, okay? Straight up. So we have an initial velocity of 15 meters per second, and I'm going to call up positive again. So I get v initial equals 15 meters per second. And the cliff is 100 meters high. Now, here's the tricky part here. If I say that this right here is my 100 meters high, This is my 0 meters, which is the ground. Now my delta y here, my change in position, will be final position minus initial position. 0 is my final. I wrote initial, but that's final, right? Because it goes to the ground. 100 is my initial. So final minus initial gives me a negative delta y. Okay, so be careful with that. Final minus initial gives me a negative delta y. And then we want to know how long does it take to strike the ground at the bottom. I want to know time. And then the other thing, of course, that we know, because it is under the Earth's influence of gravity, I know that the acceleration is equal to a negative 9.8 meters per second squared, because I said that up was positive, okay? So now that we have all this, we need to find an equation that works for this. So I have initial velocity, I have delta y, I have acceleration, and I want to find time. So the equation that works is going to be our delta y, or you're used to seeing delta x, but it's the same thing as a displacement, is equal to initial velocity times time plus 1/2 acceleration times time squared. So if we plug in our numbers, we get a quadratic. So we get delta y, whoops, I'm going to plug in numbers, sorry. We get negative 100 equals initial velocity, which is 15, times time, which we're trying to find, plus 1/2 times a negative 9.8 meters per second squared times time squared. All right, so I'm going to rearrange a little bit. Personally, when I'm doing quadratic formula, I like to have a positive a term for some reason. It's just personal preference. It doesn't really matter, but I like positive a. So 1/2 times 9.8 is 4.9. Yes, yes. You guys know I can't do math in my head. 4.9 t squared minus 15t minus 100 equals 0. So quadratic formula, you can use the fancy calculator with your little program on it. I just do it the old-fashioned way. I don't know why. X equals negative b plus or minus square root b. No, that's not b. B squared minus 4 ac all over 2a, which is 9.8. Okay, notice how I didn't put the negative on the b squared because negative is going to cancel out there anyway. And then on the bottom, instead of putting 2 times 4.9, I just know that 2 times 4.9 is 9.8 because I divided 9.8 by 2 to get 4.9. So I like to do under the square root first, so 15 squared. And then I'm going to add 4 times 4.9 times 100 because that negative and the negative ends up being positive. So I end up getting 2,185 under the square root. I take the square root of that and I get 15 plus or minus 46.74 over 9.8. Now, part of the reason I wanted to show you this is that we're solving for time here. All right, so think about what you're solving for. Whenever you're doing a quadratic with kinematics equations, it's going to be for time because this is the only quadratic really that you could ever be solving for something. So because we're solving for time, time can only be positive. So right away, I only have to solve for one of these, either the plus or the minus. It has to be the plus because you can't subtract 46 from 15 and get a positive number, all right? So we have to do only the plus 15, and then I'm going to divide that whole number by 9.8, and I end up getting a time of 6.3 seconds. All right, so that's example 2. And then last but not least, we have example 3. A boy is standing at the top of a bridge. He throws a pebble straight down into the water below at 5 meters per second, and it reaches the water below in 1.5 seconds. If we ignore air resistance, how fast is the pebble traveling when it hits the water? So again, I'm going to draw a little picture. So I have my bridge, and then here's the water below. Here's the pebble. He's throwing it straight down into the water below. All right, so you have to be really careful and really listen to what the problem is saying, okay? He's not throwing it up into the air, he's throwing it straight down into the water below. So I'm gonna call down positive. Something different, why not? So my initial velocity is a positive 5 meters per second, and it reaches the water below in 1.5 seconds, so that's a time of 1.5 seconds. And then also we wanna know how fast it's traveling when it reaches the water below. And I also know that since it's traveling under the influence of gravity, my acceleration here is the acceleration of gravity. So acceleration is a positive 9.8 meters per second squared. I used positive because I said that down was positive here. Okay, so just keep your signs consistent, you'll be totally fine. And it makes sense, right? Because we know that it's going to be traveling faster as it goes down. Because it's under the influence of gravity. All right, so the only equation that we know that has initial and final velocity, time, and acceleration is our first basic equation. So final velocity equals initial velocity plus acceleration times time. We are solving for final velocity, so our equation is already solved for what we want. And so all we have to do is plug in our numbers. So we get final velocity equals initial velocity, 5 meters per second, plus acceleration, 9.8 meters per second squared, times time, which is 1.5 seconds. Notice how this seconds cancels out with this right here, so we end up getting a meters per second. So I get 9.8 times 1.5, and then I'm going to add 5 to that, and so I get 19.7. Final velocity equals 19.7 meters per second. All right, so I hope that these examples helped you guys. If you have any questions, please feel free to email me, and I will see you in class.